Well, thank you very much for the invitation and for the opportunity to give this talk. I wish I was giving it in person, but I'd like to say that in about a month, I will be in South Korea in person, and I will give a series of lectures on roughly this topic in more detail. So I've tried to plan this talk in such a way that it stands by itself, but also is a little bit independent of the 3 lectures I'll give next month, which I'll approach in a slightly different way. Now, observables in quantum mechanics are operators, and operators can be multiplied. So in a quantum system, we can generally define an algebra of observables. Broadly, there are 3 kinds of algebras that you can make from quantum mechanical operators. For simplicity, I'm only going to consider algebras whose center consists only of C numbers. That's roughly analogous to simple Lie groups. Algebras with non-trivial center can be built out of the ones with trivial center, just like you build Lie groups, semi-simple Lie groups as products of, almost as products of simple ones. Sorry. There's a slight problem, which is I think you can't quite see. Can you see the top line on my slide? Can someone in Seoul tell me if you can see the top line? Okay. Okay. Now it's better, right? Okay. Now you're just missing a letter or two at the end, or maybe you can see it entirely. Anyway, as I said, there broadly are 3 types of algebras we can consider. There's one we take for granted in our study of quantum mechanics. A type 1 algebra has an irreducible representation in a Hilbert space. That's the usual situation in ordinary quantum mechanics. H is the Hilbert space of some quantum system, and the textbooks tell us that all bounded self-adjoint operators on H are observables. So the algebra of observables in ordinary quantum mechanics is just the type 1 algebra of all operators on H. And H is an irreducible representation of that algebra. So a type 1 algebra has pure states, which are just vectors in H, but it also has mixed states represented by density matrices. In a mixed state with density matrix rho, the expectation value of an operator A is the trace of A times rho. Now, you might ask what goes into making that consistent. We would like the expectation of a positive operator to be positive. And that's actually true if rho is a positive operator. That's why density matrices have to be positive. If rho is non-negative, then the expectation value of a positive operator like B dagger is also non-negative. Oh, sorry, and I'll explain that more precisely in a moment. Now, the expectation value of 1 is 1 in any state. So setting A equals 1 in this formula, a density matrix should have trace 1. Now, as for the function that we used when we talked about mixed states, the function that takes an operator A to its trace, it's simply the trace in the Hilbert space of the quantum mechanical system, and it satisfies this basic relation. The trace of AB equals the trace of BA. In case H is infinite dimensional, we need to put a condition on A and B so that the trace converges. The trace is a linear function on operators, and it's positive in the sense that the trace of a positive operator is positive. So these are the only properties of the trace that we really need in order for density matrices to make sense: symmetry, linearity, and positivity. For example, well, as I said, we want the expectation value of B dagger to be positive, so let's see how that's proved. By definition, the expectation value of B dagger in a state with density matrix rho is the trace of B dagger times rho. But using this property of the trace, we can bring B to the right-hand side. So this is the trace of B dagger rho B. But B dagger rho B is itself a non-negative operator. So using this property of the trace, it's non-negative. So these two properties are what we used to prove that a non-negative operator has a non-negative expectation value, which is needed for the formalism of density matrices to make sense. Now, with the help of the trace function, we can define familiar functions of a density matrix, like its von Neumann entropy, which is defined as minus the trace of rho log rho. So that's a type 1 algebra. A type 1 algebra is just a fancy way of talking about ordinary quantum mechanics. Now let's discuss a type 2 algebra. A type 2 algebra is still an algebra of operators on Hilbert space, so it has a Hilbert space representation. But it doesn't have an irreducible Hilbert space representation. So a system described by a type 2 algebra does not have quantum microstates. The quantum microstates would be vectors in an irreducible representation. However, a type 2 algebra does have a trace function that takes an operator A to its trace that's complex, linear, and non-degenerate, and satisfies the two basic conditions we needed in order for density matrices to make sense. This was one property, and the second is that the trace of a positive operator is positive. Now, abstractly, a state of any algebra is defined as a complex linear function on the algebra such that non-negative operators have non-negative expectation values. And also such that the expectation of the identity is 1. In the case of a type 2 algebra, we can describe states more explicitly. Just as in ordinary quantum mechanics, any state is associated to a density matrix. In fact, non-degeneracy of the trace means that any linear function of A, such as the function that maps A to its expectation value, is the trace of A rho for some rho, which is the density matrix. And I already explained that to prove positivity of these expectation values, we only need these two properties, this one and this one. Since those hold in a type 2 algebra, in a type 2 algebra, expectations defined this way are automatically positive. And since we have a trace, we can imitate ordinary quantum mechanics and define von Neumann entropies and other quantities of quantum information theory, which can essentially all be defined using only the existence of a trace. Now, there's a warning here. In a type 2 algebra, it's an infinite dimensional algebra, and the trace is really a renormalized trace. Likewise, this entropy is a renormalized entropy. It's an entropy from which an infinite constant independent of the state has been subtracted. So it's a little bit like entropy in classical physics. Entropy differences between different states are meaningful. A classical physicist defines entropy by relations like dE equals TdS, which tells you the change in entropy in an adiabatic process. But there's no natural absolute zero of entropy in classical physics, and a type 2 algebra is somewhat similar. There's an arbitrary additive constant in the definition of entropy. Well, what's a type 3 algebra? It's the worst case. It doesn't have an irreducible representation in Hilbert space, so it doesn't have quantum microstates. But it also doesn't have a trace function. So a state of such an algebra can't be represented by a density matrix, and there's no way to define a von Neumann entropy of such a state. But incidentally, it is possible to define relative entropy between two states of a type 3 algebra. A type 3 algebra is an algebra of operators on a Hilbert space, but unlike the type 1 and type 2 cases, there's no canonical choice of H. But no matter what H you pick, if you take a vector in H and define the expectation value of A as simply the expectation value in the state psi, it obeys the two axioms I stated for a state. It's positive for positive operators, and it's linear.
Can I ask a question?
Yes, please.
Yeah, so in this slide, you're using state in two different ways. So in the first case, you say the algebra does not have quantum microstates, but then you talk about a state in terms of a density matrix.
Yeah, I'm trying to use the term microstate for pure state.
Pure state. Okay, thank you.
A general state is, see, in the type 1 case, there are microstates, but the other types of algebras don't have microstates. They only have mixed states, which in operator language, unfortunately, are just called states. I agree the terminology is confusing, because most of us grow up thinking of states as being pure states without any elaboration.
Okay, thank you.
But here by a state is really the generalization of a mixed state. Any other questions? Now, type 3 algebras have arisen in physics mainly in two ways.
There is one more quick.
Another question?
Yes.
One question is there some way of regularization of type 2 to type 1 in some sense?
I don't have a useful answer. I think the question was whether a type 2 algebra can be regularized to type 1. Let's discuss it again after I've explained an example of a type 2 algebra in real life.
Okay.
Type 3 algebras have arisen in physics mainly in two ways. So in ordinary quantum field theory without gravity, you can take any region of space, such as the diamond shape. In this very schematic picture, M is space-time, and I've taken a diamond-shaped region, and I've called it U. U is meant to be an open set in space-time, so it's drawn as if space-time is two-dimensional, but think of U as an open set. In any open set, you can take the quantum field operators, and that defines an algebra of operators in that region. Araki showed in the 60s that the algebra of observables in a region is of type 3. This was actually nearly, or perhaps, the first really natural construction of type 3 algebras, which had seemed very exotic to the mathematicians who discovered them. A little later, Araki and Woods and others showed that in quantum statistical mechanics at positive temperature, in the infinite volume limit, the algebra of observables of quantum statistical mechanics is of type 3, even in the case of a very simple Hamiltonian. So these are the two main ways that type 3 algebras arise in physics. And they're related to each other. In a conformally invariant quantum field theory, the two types of type 3 algebra can be related by a conformal transformation. Now, this little brief summary of the properties of the three kinds of algebras is meant as background to the main part of my talk, where I'm going to be describing the observations of someone, an observer like us, who lives in a gravitating universe. However, not having a complete theory, the considerations will be semi-classical, although I won't try to define very precisely what is the range of validity. Following many authors such as Unruh, I'll model an observer by a time-like world line, the world line of the observer, which I'll take to be a geodesic, and I'll assume that what the observer can measure are the quantum fields along the world line. Well, what's the algebra of operators along a time-like world line, gamma? This question is answered by something called the time-like tube theorem. And the answer is that in quantum field theory without gravity, the algebra of operators along a time-like world line, gamma, is equivalent to the algebra of operators in a certain open set. This is the answer without gravity. So here in blue, I've drawn a portion of a time-like world line ending at the dots at the top and bottom, the black dots. That's meant to be this time-like world line gamma, in this case a partial one, although we could have taken a complete one. Then E of gamma is defined to consist of all points you can reach by deforming gamma through time-like curves, keeping its endpoints fixed. So in Minkowski space, E of gamma would just be a causal diamond, as drawn. And the time-like tube theorem says that the algebra of operators along a time-like world line, in the absence of gravity, is the same as the algebra of operators in a certain open set. Now, I think that's encouraging because it tells us that the algebra of operators along the world line is a reasonable thing to consider. It's a kind of generalization of what's usually, well, in the absence of gravity, it would be a special case of what's usually done, where you would consider this kind of open set. In generalizing to gravity, I think that the algebra of observables along the world line is more natural than the algebra of operators in an open set. Because for one thing, with space-time fluctuating, it's hard to say which open set you would be trying to talk about. So we're going to consider an observer who has a time-like world line gamma, and what the observer measures are the operators along the observer's world line. And will be guided by the fact that, at least in the absence of gravity, that would be equivalent to measuring all the operators in this open set. Now, if the observer has causal access to a complete initial value surface, for example, if the observer is living in an asymptotically flat spacetime, something that looks at infinity like Minkowski space, but inside there are stars and galaxies. If you wait long enough in such a spacetime, you see the whole universe, the whole initial value surface. So in such a case, a whole initial value surface is contained in the region the observer can see. And in that situation, taking causality into account, the algebra accessible to the observer would then really be all operators in Hilbert space. So you would think it would be presumably the type 1 algebra of all operators. So in an asymptotically flat spacetime where the observer can see the whole universe, I expect this construction will just give a type 1 algebra. For today, we're more interested in a case in which, because of past and future horizons, the observer does not have causal access to a complete initial value surface. In such a case, as was probably first said by Stephen Hawking, one would not expect the observer to be able to resolve quantum microstates. So you would not expect to be able to describe what the observer sees by a type 1 algebra. You should expect the operators accessible to the observer to be of type 2 or type 3. Now, Stephen Hawking claimed that observations of an observer whose vision is limited by horizons would be described by a density matrix rather than a quantum mechanical pure state. It's not clear to me whether either Hawking or others who have made similar statements later on took this as something that's supposed to be literally true or just as a metaphor. But from what I've told you, you can see that if it's supposed to be literally true, it means that the operators accessible to the observer should form an algebra of type 2, not of type 3. Today, I want to explore this question and to explain how to demonstrate that it's actually true in one important case, which will involve de Sitter space. There'll be a much more complete explanation in my in-person lectures at the Asia, sorry, I think I have the initials in the wrong order, APCTP, Asia Pacific Center for Theoretical Physics, next month. So those of you who will be in Korea next month, if you wish, can hear about this in much more detail. And the rest of you online, I think. What I'll say is adapted from two papers. The first paper written a year ago on this special case of de Sitter space, and a more recent paper in which I've reconsidered the construction from a different point of view. Though I won't quite be able to fully explain that today. What I'll explain today is a mixture of what was in the two papers. Now, some preliminary remarks. First, it's very important that I want to think about an observer like us who has no a priori knowledge of the universe and only knows what's been learned from observation. A priori, the observer has no idea of what universe the observer is living in. To describe this situation, we have to define an algebra that's universal and background independent, with no reference to any particular spacetime. If the definition of the algebra depends on the spacetime, then we're putting in information that the observer doesn't have. Now, there is also a literature on cases where the observer is assumed to have a priori knowledge of the universe, and then things are completely different. But in today's lecture, we consider an observer who knows nothing except whatever is observed. Second, we expect that in a full theory of quantum gravity, an observer cannot be introduced from outside, but must be described by the theory. Of course, in an asymptotically flat or asymptotically anti-de Sitter spacetime, there are asymptotic observables at infinity. And you can have an observer at infinity who probes spacetime from outside. A more typical example for today's lecture, though, is a typical cosmological model that can't be probed from outside in any sensible way. The only observers are observers like us who live inside the spacetime that's being observed. Now, in a full theory, an observer who lives in the spacetime must be described by the theory. So what does it mean to assume the presence of the observer? What it really means is that we will define an algebra that makes sense in a subspace of states in which an observer is present. We won't try to define an algebra that makes sense in all states. First, let's consider an observer in the absence of gravity. As I've said, the observer propagates in a spacetime M on a geodesic gamma. I've drawn the geodesic as being curved because the spacetime might be curved, but it's a fixed spacetime with no dynamical gravity. The world line can be parametrized by the observer's proper time measured along the world line. What the observer measures might be, for example, a scalar field phi, or the electromagnetic field F mu, or the Riemann tensor, as well as covariant derivatives of all of these in normal directions. Let's pick a particular observable, for example, a scalar field phi, and the observable is really phi evaluated at the position x where the observer is at time tau. But I'll just abbreviate that as phi of tau. So in the absence of gravity, phi of tau is a sensible observable. What changes when we take gravity to be dynamical? Well, we have to consider that the same world line can be embedded in a given space-time in different ways, differing by tau going to tau plus a constant. So it was a little oversimplified when I said that proper time, the world line can be parameterized by proper time. That's true, but there's no natural zero of proper time. The observer picks an arbitrary point to be the zero of proper time, and then measures the proper time as positive to the future of that, negative to the past. But in the presence of gravity, we have to realize that diffeomorphisms shift the points, and in particular, there's no natural point to be the zero of the proper time. So 5 tau isn't by itself a meaningful observable. We need to introduce a clock. We need to introduce observer's degree of freedom, but the bare minimum we need for today is to give the observer a clock. And then we have to define tau relative to the observer's clock. So in a minimal model, I'll give the observer nothing except a rest mass. Well, I'll give the observer a Hamiltonian, which have a constant piece, the observer's rest mass, an additional contribution Q, that I'll call Q. I'm going to assume that the observer energy is bounded below, so Q will be non-negative. That makes M the observer's rest mass. And there's a canonical variable P, which is minus ID by dQ. However, if we want Q to be non-negative, we have to only allow operators that preserve this condition. So for example, e to the IP is not a good operator because it does not preserve the condition that Q is non-negative. It should be replaced by pi e to the IP times pi, where pi equals theta of Q is the projection operator onto Q non-negative. So all our operators, I'll write operators without worrying that Q is non-negative, but then I cure them by sandwiching them between two pi's. Well, now we want to allow only operators that commute with what I'll call H hat, which will be the sum of H bulk plus H observer. H observer is this Hamiltonian of the observer. But H bulk is any gravitational constraint operator that generates a shift of tau along the world line. So H bulk is any diffeomorphism of spacetime that moves the observer forward in time by a constant amount along the world line. I'm not telling you what H bulk does away from the observer world line, and in general, there's no natural choice. But the choice doesn't matter because diffeomorphisms that are trivial away from the world line will anyway be imposed as constraints. So we've already imposed all the other constraints away from the observer world line, and then we impose one more constraint that shifts the observer together with the ambient fields forward in time by a constant amount. So we only want to allow operators that commute with this constraint operator. Now, H bulk generates time translation, so H bulk commuted with phi is minus I phi dot. And H observer is a C number MC squared plus Q. So we need Q commuted with phi to be I phi dot plus I phi dot. Now, since Q is canonically conjugate to P, Q is I d by dP, although I didn't write that. I did write the converse that P was minus I d by dQ. So Q is I d by dP. So if I just set tau equals P, or more generally, tau equals P plus a constant, then I'll get this desired relation. I'm having trouble highlighting this equation. I'm attempting to highlight this. Okay. So to satisfy this highlighted equation, I can simply set tau equals P, or more generally, P plus a constant. So a typical allowed operator is phi of P plus S, except that wouldn't commute with the constraint that Q is non-negative. So taking that into account, I put the projection operator pi before and after, and this is a typical allowed operator. So it's theta of Q, phi of P plus S times theta of Q. So these are good operators along the observer world line in the presence of gravity. In addition to these operators, with phi possibly replaced by some other field, like the electromagnetic field or the Riemann tensor, there's one more obvious operator that commutes with the constraint, namely Q itself. So we define an algebra A of the observer, A sub observer, that's generated by the operators we've mentioned. You can actually show there are no other good operators. Now, I said that to give a satisfactory account of physics as seen by an observer who knows nothing except whatever is observed, we need an algebra that's background independent. What I've said so far hopefully sounds background independent, since we described it without picking a background. I didn't say anything about the space-time that the observer was living in or what the geodesic was. However, background independence really depends on interpreting the formulas properly. We will not get background independence if we interpret phi hat and Q as Hilbert space operators. To get a Hilbert space in which they act, we have to pick a space-time M in which the observer is propagating and also a geodesic in which the observer propagates. But if we have to pick those to get a Hilbert space, we won't have background independence. To get background independence, we have to think of the algebra of the observer as an operator product algebra rather than an algebra of Hilbert space operators. Then, as an operator product algebra, it's universal because the short distance singularities are universal and don't depend on any knowledge about the space-time the observer is living in. The algebras for different m's are then inequivalent representations of the same underlying operator product algebra. So to underscore this a little bit, in the absence of gravity, we'd characterize the objects phi of tau by their universal short distance singularities. The leading one has a coefficient which is the identity. They're higher order terms involving all kinds of local operators along the world line, including, for example, the Riemann tensor and its covariant derivatives. As long as we include all possible operators as terms that can appear on the right-hand side of this expansion, the expansion can be defined universally with no knowledge whatsoever of the space-time the observer lives in. That was in the absence of gravity. After coupling to gravity and including the observer in the constraint, the short distance expansion in powers of tau minus tau prime actually becomes an expansion in 1 over q. But it still has the basic property of being universal. So we characterize a observer purely by the universal short distance or 1 over q expansion of operator products. Without understanding its background independent. This might be a good time to stop for questions, if there are any.
No questions. But, Edward, could you tell us, okay, in this case, if you are considering these local quantities, right, as observable things, then it's some kind of universal pattern. For instance, tau goes to tau strich. How can you feel curvature in this case?
You feel curvature because the Riemann tensor is one of the operators that appears on the
But
right.
Riemann tensor will be actually next to the, will give you next to the correction for curvature because it
Oh,
involves derivative.
I only wrote the first term. We can,
Yeah, but here there is no Riemann tensor, right?
I
In
didn't.
such kind of quantities, because
No,
it will be.
no, you're mistaken. There is. There was the term tau minus tau prime minus I epsilon to the minus 2 delta plus 2 times the Riemann tensor.
Plus the Riemann tensor, yeah. Okay,
Plus
but
dot dot dot. When I write plus dot dot dot, I mean all the possible terms and operators that can appear there. Everything we study in physics, the electromagnetic field, the electromagnetic current, the Riemann tensor, the 10th covariant derivative of the Riemann tensor will appear in order minus 2 delta plus 12 and so on.
but the leading term should be like in Minkowski space, right? Because of equivalence principle.
The leading term is as in Minkowski space.
Yes. Huh? It's like Minkowski, yeah.
Leading
So,
term is in Minkowski space.
yeah.
But the algebra we're describing is not limited to the leading term. We're not talking about the leading term. We're talking about the OP expanded to all orders.
Okay, thank you.
Any other questions? Okay.
Since no more questions.
Now, similarly to what I said in the abstract discussion for the algebras, by a state of the observer algebra, we mean simply a linear function which satisfies two conditions. One, it's positive in the sense that the expectation value of O dagger is non-negative for all O. And two, it's consistent with all universal OPE relations. This is analogous to a definition given by Holland and Wald for quantum field theory in a fixed curved space-time background. If M is any space-time in which the observer may be living, along with some geodesic, and H is the Hilbert space that describes fields in M together with the observer, and psi is a state in H, then the function that takes O to its expectation value in the state psi is a state of the algebra by the definition I gave. Now, these definitions make sense for any M, but they're most interesting when, because of black hole or cosmological horizons, the part of the universe the observer can see does not include a complete Cauchy hypersurface. Now, there's a special case that turns out to be important that I want to describe in detail. Actually, it's the main thing I'll describe in the rest of today's lecture. I'll go into a more general story when I'm in Korea in person next month. The special case I want to talk about is the case that M is an empty de Sitter space with some positive value of the effective cosmological constant. So here's a Penrose diagram. In the Penrose diagram, future infinity is the blue line at the top, past infinity is the blue line at the bottom. Coordinates on the Penrose diagram can be picked so that the left, well, first of all, the left boundary in the diagram is a geodesic. And I've drawn the Penrose diagram so that the left boundary is the world line of the observer. You can see then that, as was shown by Gibbons and Hawking, what the observer can see is bounded by past and future horizons, which are these red lines, red diagonals. And what the observer can actually see is this shaded green triangle. The green region is called a static patch because it's invariant under a particular de Sitter generator H that advances the proper time of the observer. And that means that when I was previously constructing the algebra, I said that you pick some bulk constraint operator, but in general, there's no natural choice. In de Sitter space, there actually is a natural choice, that the constraint operator that we used can be the de Sitter generator that's a symmetry of the static patch and moves the observer world line forward in time. In the absence of gravity, there's a distinguished de Sitter invariant state psi ds, such that correlation functions in this state are thermal at the de Sitter temperature. Now, what exactly does it mean to say that correlation functions are thermal? It can be summarized by two key properties, which I'll state for 2-point functions, but they can be generalized for n-point correlation functions. The 2-point functions have two key properties. The first is simply time translation symmetry. The second key property is more subtle. It's called the KMS condition. It says that if you exchange the order of two operators, using time translation symmetry, I can assume that one is inserted at proper times at tau equals 0. The other is inserted at some proper time tau. The KMS condition says that we can reverse the order of the two operators if we shift tau by minus I beta. A precise statement involves the fact that the left-hand side is holomorphic in a strip in the complex plane. And you analytically continue it to the boundary of the strip, and then it's equal to this. So I'm not quite set up to write on these slides at the moment. I'd have to share from my iPad to do that. The KMS condition for an ordinary thermal system follows directly from the definition of thermal correlation functions involving the density matrix. The density matrix being e to the minus beta h. A short calculation leads to the KMS condition, as was originally shown by Kuba, Martin, and Schwinger. Not that precise proof does not apply in de Sitter space, but using the fact that the state correlations in the function in the state psi ds arise by analytic continuation from Euclidean space, one can show that the KMS condition holds. So these statements are the precise meaning of the assertion that correlators in the state psi ds are thermal at the de Sitter temperature. Now I want to explain what happens to those properties after you include the observer, couple to gravity and include the observer. Well, when we include gravity in the observer, we have to combine the state psi ds with some state of the observer. And it turns out that the natural state to consider is one in which the observer energy has a thermal distribution at the de Sitter temperature. So what I've written here is simply a state where the observer energy is thermally distributed. So if you like, the observer is in equilibrium with the quantum fields. And we replace operators phi of tau that appeared in this page with their gravitationally dressed versions. Then a straightforward computation shows two facts. One is we still have time translation symmetry, except it acts on the constant that I used in defining these operators. Well, the constant appears here. It acts on that constant shift in the time, shifting S and S prime by constant C. But what's more interesting and dramatic is that the KMS condition simplifies. The KMS condition in ordinary thermal physics and also in de Sitter space without gravity says this, with a very important shift by minus I beta. But after including gravity, the shift disappears. And the KMS condition says that we can simply reorder the two operators. I'll give you a proof in a little while, but let's discuss the consequences. This condition 2 prime means that if I define the expectation value of an operator in the state psi max, which remember is the de Sitter invariant state together with a thermal distribution of the observer energy, if I define that to be the trace of A, then you see that the trace does have the algebraic property of a trace. That's precisely what condition 2' said. The trace also is positive because the trace of A dagger would be the expectation value of the trace of A dagger A would be the expectation value of A dagger A in the state psi max, but that's the same as the norm squared of the state A on psi max, so it's non-negative for all A. And I normalize the state psi max to be a unit vector. That's what we got out of this constant here. And since it is a unit vector, this definition implies that the trace of the identity is 1. So if we can prove condition 2', that will mean that for the observer in de Sitter space, the algebra, including gravity, is an algebra of type 2. It has this trace. So I'll prove that key property soon, but first I want to explain the consequences. Let H be the Hilbert space that describes quantum fields in de Sitter space along with the observer. To any state psi in H, we can associate a density matrix using the non-degenerate trace. This should have been TR rather than rho here. In other words, because the trace is non-degenerate, any linear function of an operator, such as this one, is the trace of A times something, which is the density matrix of the state psi. So every state will have a density matrix. And for example, we know immediately the density matrix of the state psi max, because by definition, the expectation value of the operator A in the state psi max is equal to the trace of A. So that tells us that for the state psi max, this condition is obeyed with rho equals 1. So the density matrix of the state psi max is 1. Similarly, you can consider a state, which I'll call psi b hat, which is b hat times psi max, where b hat is any operator in the observer algebra. It's a nice exercise to show that the density matrix of that state is b hat dagger. All you need to use is the basic property of the trace of AB equals the trace of BA. States of the form psi b hat are actually dense in Hilbert space, so this is an explicit proof that a dense set of states, and therefore all states by taking limits, have a density matrix. Now, as we discussed earlier, once we have traces and density matrices, we also have entropies. We can immediately compute the entropy of the state psi max, whose density matrix is 1. Since the logarithm of 1 is 0, the entropy of rho max is minus the trace of 1 log 1, or 0. It turns out that all other density matrices have strictly negative entropy, so psi max is a state of maximum possible entropy. Now, one way to prove that every density matrix other than 1 has negative entropy is the following. Let rho be any other density matrix. Then, for t between 0 and 1, let rho sub t be a linear combination of 1 and rho, whose trace is 1. It's positive and has trace 1, so it's also a density matrix. And then let f of t be the entropy of rho sub t, or minus the trace of rho t log rho t. So the quantity we want, S of rho, is f of 1, because at t equals 1, rho t equals rho. Now, you can, well, there are a couple of steps you can write by elementary calculus. First of all, although I didn't write it, f of 0 is 0, and also f prime of 0 is 0. Slightly less trivial, but not hard to prove, is that f double prime is negative. To prove that f double prime is negative, you use this formula for the logarithm of an operator. And then you can compute for f double prime a formula which is manifestly negative, because it's minus the trace squared, the trace of a self-adjoint operator squared. So since f and f prime of 0 are 0 and f double prime is negative, we find that f of 1 is negative. So every density matrix other than 1 has negative entropy. So the system consisting of an observer in a static patch in de Sitter space has a state of maximum entropy consisting of empty de Sitter space in equilibrium with the observer. Now, that empty de Sitter space has maximum entropy has been claimed in the past with a variety of arguments, going back to the fact that placing a black hole in the static patch actually reduces the entropy. A black hole has a big entropy, but if you put a black hole in the static patch, which you might think increases the entropy, the gravity of the black hole reduces the area of the horizon. And as Gibbons and Hawking taught us, the horizon area should be viewed as a cosmological entropy. And these authors showed that the total horizon area of the black hole plus the horizon is less than would have been the horizon entropy of empty de Sitter space. So this was the first argument that empty de Sitter space has maximum entropy, and other arguments were given later, of which I'll mention one in a moment, I think. So here we've arrived at what you might regard as a very general abstract proof that empty de Sitter space has maximum entropy. A difference, though, is that we have a precise definition of entropy. The entropy we're talking about is the entropy of an algebra, the entropy of a state of an algebra. And we have a precise proof that this particular state, which is empty de Sitter space extended to include the observer, is a state of maximum entropy. Now, these authors gave the first indication, but a couple of years later, the first general argument was given by Busso, who argued that this must be true based on the second law of thermodynamics, because the static patch is empty in the far future. A generic particle in this green region will exit through the future horizon. So in the far future, the static patch will be empty. And then Busso argued that according to the second law of thermodynamics, the system must be evolving in a way that increases the entropy. And since it's empty in the far future, since any starting initial state, no matter what it is, will evolve to empty de Sitter space, he concluded that since anything evolves to empty de Sitter space, he concluded that empty de Sitter space has maximum entropy. It's a very nice argument. And notice that it didn't require any conceptually clear definition of entropy. Just like in the 19th century, entropy was originally discovered by Carnot without any microscopic understanding whatsoever. The slight difference from the way I'm presenting it today is that we do have some microscopic understanding because we've defined an algebra and a state of an algebra and a precise definition of entropy such that it was true that empty de Sitter space extended to include the observer, thus have maximum entropy. Let's consider Busso's argument in the context of today's discussion. Well, Busso simply said that the static patch is empty in the far future. But in the present context, we've defined the static patch by the presence of the observer. So by definition, the observer doesn't leave the static patch even in the far future. But we can expect that in the far future, the static patch will be empty except for the presence of the observer, and that the observer will be in thermal equilibrium with the bulk quantum fields. And that's what we see in the state psi max. So the maximum entropy state that we found is the one suggested by Busso's argument. Now, if you consider states other than the maximum entropy state, it's possible to show that entropy defined as I've explained agrees up to an additive constant independent of the state with the usual definition of the generalized entropy for a suitable class of semi-classical states. The argument involves comparing to a description of the generalized entropy by Wall. The constant discrepancy is simply that in this approach, the maximum entropy is defined to be 0, rather than the usual de Sitter entropy, which is horizon area over 4G plus logarithmic and subleading corrections. So here we have a microscopic framework for defining entropy, but the maximum entropy has been subtracted from all entropies. A limitation in this comparison of the entropy defined algebraically to the generalized entropy we're only seeing contributions of order 1, not 1 over g, from the a over 4g term. It would be much nicer to eliminate this restriction. I won't have much time to talk about today, but I will say more at the ACPTP lectures next month. Now, it is a serious drawback that entropy defined this way is a renormalized entropy from which an overall constant independent of the state has been subtracted. So as I said already, the entropy of the maximum entropy state was set to 0, while it's natural to assign to it a large value, a over 4g. If we consider instead of de Sitter space some other spacetime M and we're able to repeat the analysis, we'll again get a definition of entropy, again after an additive constant. It's not satisfactory to have a new additive constant for each spacetime. That leaves us unable to compare the different spacetimes. We'd rather at least have a definition of entropy with only one overall renormalization constant, independent of the spacetime. I suspect that's the best you can do in a picture based on algebras rather than quantum microstates, which possibly means in any picture in which semi-classical ideas make sense. But anyway, so in next month's lecture, I'll say more about this, but I won't have time to say very much today. What I do want to do is to go back and prove the key tracial condition 2 prime, that the trace of a hat b hat equals the trace of b hat a hat. Now, the purpose of proving it for you is to convince you that it's elementary. It's only going to take a few slides, and they will be elementary calculations of a type you're all quite familiar with, and I'm only going to use facts you all know. But it might be a little bit hard to follow it when it's presented on the screen. However, I hope to at least convince you that no fancy math is involved, it's only based on things that you know. As an example, I'll take A and B to be constructed from local operators. Well, I'll start with, in the underlying algebra without gravity, I'll let A and B be local operators at some times S and S prime. Then, including the observer degrees of freedom and opposing the constraint, we replace A and B with their addressed versions, where A of P and B of P are defined this way. H is the time translation generator in the static patch. So now I want to prove that the trace of A hat B hat equals the trace of B hat A hat in such a way that no information about von Neumann algebras is required. I only will use facts that you all know. So I want to prove this statement using familiar facts. Well, first of all, because the state psi max is annihilated by H, and also is invariant under pi, what we want to prove simplifies to this. Now, the form of this relation suggests it's convenient to use a representation in which P is a multiplication operator and Q is ID by dP. Because we have these operators A of P and B of P, which are easier to understand if P is a multiplication operator rather than if it's supposed to be a derivative, differential operator. So if P is a multiplication operator, then pi, which projects onto positive Q, becomes an integral operator, which is this one. And the state psi max can also be represented in the P basis this way. So using those facts, you find that the quantity we're trying to calculate can be written in the P basis in a way that involves integrals over P and P prime. And the integrand has an explicit rational function, and it also has an ordinary 2-point function in the de Sitter invariant state without gravity. You can think of P and P prime here as just being the times at which we measure the 2-point function in the de Sitter invariant state. Now we can use ordinary time translation symmetry, which says that this is only a function of P minus P prime. So I let V be P minus P prime, and this expression here takes this form, where now you notice that you can integrate explicitly over P and reduce to a one-dimensional integral. At this stage, we just have to use holomorphy and the KMS property, which was condition 2 in the absence of gravity. So holomorphy means that the integrand in this expression is holomorphic in a certain strip, and therefore you can shift the integration contour from the real v-axis to displace it by an amount I beta in the complex plane. And after shifting it, you can then invoke the KMS property, and you get this expression here. Oh, sorry, just by shifting the integration contour, you get this expression. Then when you use the KMS property and also set v equals minus w, it turns into this thing here. And after one more use of time translation symmetry to replace the minus w here by a plus w here, and this becomes 0, you see that the right-hand side, you see this formula, see that the right-hand side of this, sorry, you see that the right-hand side of this expression looks just like the right-hand side of this expression, except with b and a exchanged. So finally, you complete the proof. You learn that this expression here is unchanged if you, sorry. I've written two equations on this slide. One is here and one is here. Up to the KMS property and time translation symmetry, the two just differ. Sorry. The two just differ by exchanging A and B. So that completes the proof. Although I think I stumbled a bit at the end. Now, it'll probably be easier to follow these steps if you look at the paper where a little more detail is given. But even if it's been hard to follow the details, I hope to convince you there is no exotic math. Only basic properties of the de Sitter invariant state that we had before including the observer uncoupling to gravity. So we have a very explicit framework for defining entropy and proving that empty de Sitter space in equilibrium with the observer has maximum possible entropy. A further remark. In a more speculative vein, which I'll explain in more detail in next month's lectures, one can try to generalize some aspects of this to an arbitrary spacetime by using the Hartle-Hawking no boundary state rather than the de Sitter invariant state. The de Sitter invariant state is formally a sort of approximation to the Hartle-Hawking state with gravity turned off. So I think I'm going to have to stop here.